All right, let's talk about something that could completely change our world, the solid-state battery. We're talking about the holy grail of energy storage. Think about an electric car that could drive from New York to LA on one charge, or a smartphone that lasts for days, not hours. It sounds like science fiction, right? Well, it's closer than you think. But to get there, scientists are fighting a massive battle on an atomic scale. So let's start with the problem they're trying to fix.
You know, to really get where we're going, we gotta look at where we are right now. And let's be honest, you felt this, I've felt this, we've all felt the pain of today's batteries. You know the feeling, right? That frantic daily search for a charger, the pit in your stomach when your EV's battery warning flashes, or just watching your expensive phone slowly die a little more with every single charge. These aren't just little annoyances, they're the fundamental bottleneck. They're what's holding us back from the next giant leap forward in everything.
So what's the real problem here? Well, it all boils down to what's going on inside the battery. The lithium-ion batteries in everything we own today, they use a liquid electrolyte. You can basically think of it as a flammable, reactive soup that shuttles ions around. The big idea with solid-state tech is to replace that soupy liquid with a solid. And the difference is, well, it's night and day. You go from something that can catch fire to something that won't. You get rid of the risk of thermal runaway, that's a fancy term for a dangerous fire, and you get enhanced safety. But the real game changer? You unlock the door to way more energy density and a battery that can be charged again and again and again without fading.
Okay, let's really dig into this bottleneck. The problem isn't the lithium itself. The lithium ions are doing their job just fine. The problem is the messy, dangerous environment they have to swim through. That liquid electrolyte got us this far, for sure, but we have basically pushed it to its absolute breaking point.
And what's really wild is how all these problems are connected. So those organic solvents that make the liquid work, they're flammable by nature. That's a huge safety risk, especially when you're talking about a massive battery pack in a car. But it gets worse. This liquid is also chemically unstable. Over time, it starts reacting with the electrodes and forms these crusty layers. It's kind of like plaque building up in an artery, slowly choking off the flow of energy. That's why your phone battery gets worse over time. And to top it all off, since it's a liquid, you need all this bulky, heavy packaging just to keep it from leaking. All that weight and space adds zero power.
So if the liquid is the problem, the solution seems pretty obvious, doesn't it? Just make it solid. And that is the beautifully simple idea.
Which brings us to the million-dollar question, right? If this stuff is so great, why isn't there a solid-state battery in my phone or my car right now? Well, the answer is that creating a perfect solid-state battery is one of the toughest material science puzzles of our generation. The real war is being fought at the atomic level, in a world so small it's almost impossible to imagine.
So here's why it's so incredibly difficult. It all happens at the interface. You know, the place where the solid electrode actually touches the solid electrolyte. At that microscopic meeting point, a whole bunch of tiny, destructive things can go wrong. And figuring out how to control those interfaces, well, that's the whole ballgame.
So check this out. This diagram from the research at TU Delft, it's perfect. It's like a most wanted poster for all the bad guys in our story. Over on the left, where the anode and the electrolyte meet, you've got villains like dendrite formation and these nasty interphase layers. Then you look over on the right, at the cathode side, and you've got the same kind of trouble. Things like contact loss and just general chemical chaos. And look, these aren't just sciencey words on a chart. These are the real physical things that will literally kill a solid-state battery if you let them.
Let's talk about public enemy number one, lithium dendrites. I want you to picture these tiny, super sharp needles made of pure lithium metal. As the battery gets used, these little metal spikes start to grow out from the anode, and they can actually force their way through the solid electrolyte, kind of like a tree root cracking through solid concrete. If just one of those dendrites makes it all the way to the other side, boom, you get a short circuit and the battery is toast. And it can fail in a really, really bad way. Stopping these things from ever forming is priority number one.
So really, the whole challenge boils down to these three massive hurdles. First, you have to stop those dendrites from creating a killer short circuit. Second, you have to solve a physics problem called contact loss. I mean, how do you keep two solid things pressed together perfectly when they're constantly expanding and shrinking? And third, you have to master the chemistry of interface instability. You got to stop that resistive gunk from forming and suffocating the battery. You can't just solve one or two. A working battery has to beat all three all at once.
For years, honestly, these problems seemed like they might be impossible to solve. The materials just didn't look stable enough to even work in the real world. But then there was this huge breakthrough in just understanding the problem. It turned out it wasn't about finding some magical, perfect material. It was about realizing everyone was looking at the problem completely wrong.
See, the early calculations, the ones based on thermodynamics, they all predicted that most of these solid materials would basically just disintegrate at the voltages you need to actually run a battery. The models were screaming that these materials were fundamentally unstable. It was a pretty grim forecast, and it made it seem like this whole solid-state thing might just be a dead end.
And this chart really shows you the breakthrough moment. The old models, which were based on this idea of direct decomposition, they predicted this tiny, useless stability window of just 0.3 volts for a popular material. But then, new research came out of TU Delft showing that the material doesn't fail directly, it fails indirectly. And this new way of looking at it revealed a much bigger, practical stability window of 1.25 volts. Now, it's still not perfect, but it was a window you could actually work with. It was hope.
So what does that actually mean? Well, the old theory basically assumed the solid electrolyte would just shatter instantly into its most stable parts, like a glass turning back into sand. The new insight was that it doesn't happen that way. First, it transforms into this weird, temporary in-between state, a metastable phase. And getting to that state requires a different amount of energy, which defines the real-world operating window of the battery. It was like suddenly realizing the field you're playing on is way bigger than you thought. This was the big aha moment.
Okay, so, armed with this totally new understanding, scientists could finally stop searching for a mythical, perfect material and instead start intelligently engineering systems that could work inside this new, much more realistic window.
And this has led to this awesome two-pronged attack on the problem. First, we have smarter materials, where we're making tiny, super precise tweaks at the atomic level. And second, we have smarter engineering, where we're using powerful computers and brand new manufacturing methods to design batteries that we couldn't even have dreamed of a decade ago. So let's look at the smarter materials idea first, using a trick called doping. Research showed that in one of these electrolytes, the lithium ions had a favorite path to take, but there was a slow spot, a traffic jam. So what do? They strategically swapped out a few atoms. In this case, they replaced some phosphorus with silicon. It's an unbelievably elegant fix. The new silicon atom basically acts like a construction crew, opening up a brand new superhighway for the lithium ions, so they can just cruise right past the original traffic jam.
And we're not talking about a tiny little improvement here. This one clever atomic-level substitution can boost the ionic conductivity, that's just the speed of the ions, by 3 times, a 3x improvement. It's a perfect example of how once you really understand the problem, you can make these tiny, precise changes that have a massive impact.
Then you have the second strategy, smarter engineering. Instead of just mixing stuff up in the lab and hoping for the best, scientists are now using these insane computational models. We're talking quantum mechanics to predict how a material is going to act before they even make it. It lets them test hundreds of ideas on a computer first. At the same time, you've got amazing new technologies like 3D printing that let us build batteries with totally new internal structures, all optimized to squeeze out every last drop of power.
So, with all these incredible breakthroughs in both the basic science and the engineering, where are we? When can we actually get our hands on these next-gen batteries? Well, the path is getting clearer every day, but it's still a tough road ahead.
This table gives us a really great snapshot of what the experts think. Best case scenario? We could see mass production getting prices down to around $140 per kilowatt hour by 2028. That's not too far away. Now, the more cautious view says manufacturing challenges could push that out to the early 2030s. But here's the key. Commercial production isn't a pipe dream anymore. It is officially on the roadmap.
And this quote from a recent paper really nails why this is all so important. They call it a strategic step toward achieving safer, more reliable, and sustainable electric mobility. This isn't just about our phones lasting longer. This is about making electric cars safer, more practical, and affordable for everybody. It's about building a cleaner, more stable energy future.
So at the end of the day, we're left with this. The science is pointing the way. The engineering is solving the puzzles. The question is no longer if solid-state batteries are coming, it's when. And when they get here, when your car can charge in 10 minutes and drive 1,000 kilometers, when your phone lasts a whole week, what new things will that make possible? What are you going to do with that power? That's what makes this one of the most exciting stories in science today.